Alright, so we have a function f which is differentiable, and it's invertible, and its inverse is differentiable. If this is the case, you might wonder, what do we know about the derivative of f inverse? And it turns out we know a lot. In fact, we know exactly what it looks like, and that's what we want to prove. Okay, so the first thing to note here is that this thing here, f inverse prime of a equals this f prime of f inverse a inverse, this is not 1 over f prime of f inverse a, because these are matrices. And so we want to prove that these two matrices are equal. And so to prove this, we must prove that let's see here. So we need, not only do we need, so we need this f inverse prime of a to be the inverse of the matrix on the right. So what that means is that if you take the thing on the right, remove the inverse, and multiply it by the thing on the left, you get the identity matrix. And you need to prove that that holds no matter which order you're multiplying the matrices, because, of course, matrix multiplication is not necessarily commutative. It's obviously commutative if the two matrices, if their product is the identity matrix. But until you know that these two matrices are the inverses of each other, you don't know for sure that the matrices commute. Or you don't know for sure that that the matrices commute with respect to multiplication. So anyways, what we need to prove is we need to prove both f inverse prime of a times f prime of f inverse a is the identity matrix I, and we must prove the exact same thing, but if we multiply them in the other direction. F inverse prime of a equals I. Okay. Now, since f is differentiable, so let's see here. F is differentiable, and it has a differentiable inverse. So it has an inverse. So f is invertible. So for all x, if we take f of f inverse of x, well, this is just going to be x. And then if we take the derivative of this equation, we just, on the left-hand side, we use the chain rule. So we start with f prime of f inverse of x, and then we multiply by f of, then we multiply by the derivative of the thing on the inside, and the thing on the inside here is f inverse of x, so we multiply by f inverse prime of x. And this is I. Yeah. So that's one of them. Also, for all x, we have the same thing in the reverse or you can change the order of the two functions here because the functions are inverses of each other. So f inverse of f of x equals x. And so if we take the derivative of this equation, we get f inverse prime of the thing on the inside, f of x, times the derivative of the thing on the inside, f of x, equals I. This holds for every single x. So in particular, so here, so let x equals a. Also, because the thing before we had f prime of f inverse x times f inverse prime of x equals I. And that holds for all x, so in particular it holds for a. Well, I guess Oh, well, I guess for this particular example, it doesn't really matter that we're using x's and a's here. We're just trying to prove that these two functions, or these two matrices, are the same thing for any a. And so it doesn't matter if you call it x or if you call it a. But the reason that we're using two variables is that for the second part, we have to do a transformation. And so if we want to get this thing to look like the other equation that we have, we need to set... What do we need to set? So we need so we have this f inverse prime thing, and we need to evaluate at a. So we need a to be f of x. So if we want a to be f of x, let a equals f of x, i.e., if you solve for x, x is f inverse of a. Then what we get is we have f inverse prime of f inverse prime of a equals, times, and now this is going to be f prime of x, which is f inverse of a. This is the identity. Okay, so if we take f inverse prime of a times f prime of f inverse of a, then we get the identity. And if we take f prime of f inverse of a times f inverse prime of a, we get I. So you multiply these two matrices together in any order, you get the identity matrix. So thus, that's what it means for this matrix to be the inverse of this matrix. And so then we are done.